Have you ever stared up at the night sky and wondered if we are truly alone in the universe? For centuries, humanity has searched the stars for signs of life beyond our own. But what if the answer has been hiding right next door all along? On the rust-red plains of Mars, scientists have uncovered a mystery so compelling, so baffling, that it may just rewrite our understanding of life itself. Methane, a gas often produced by living organisms here on Earth, has been detected swirling through the thin Martian atmosphere in unpredictable, tantalizing bursts. This isn't just some scientific footnote. It's a cosmic clue that has researchers around the globe leaning forward in excitement, daring to ask one of the most profound questions we can pose. Could there be alien microbes breathing beneath the surface of Mars right now? Think about that for a moment. We're not talking about little green men or intergalactic civilizations. We're talking about the possibility of life in its most humble, yet most resilient form, microbes, quietly existing in the harsh, cold soil of another world. It's a thought that sparks something deep within us, something between wonder and recognition. Because if life can take hold not just here but there, what does that say about our place in the cosmos? The detection of methane on Mars isn't just a chemical curiosity. It feels like a whisper from the universe, a hint that we may be on the verge of one of the greatest discoveries in human history. It's a story of persistence, of cutting-edge technology meeting age-old curiosity, and of the thrilling possibility that we are closer than ever to answering a question that has haunted philosophers, scientists, and dreamers for generations. In this video, we're going to dive deep into the heart of this mystery. We'll explore how we first detected these enigmatic methane signals, what they might mean, and why they've set the scientific community ablaze with theories ranging from geological processes to, yes, the potential presence of living organisms. You'll come away not just with facts, but with a sense of what it means to be part of this moment in exploration, where every new Rover mission and every atmospheric reading brings us one step closer to perhaps the most staggering revelation imaginable. So settle in, open your mind, and join me on a journey to the Red Planet, where a gas we take for granted on Earth might just be the key to unlocking the secrets of life beyond it. So let's break down exactly why this one molecule is causing such a cosmic commotion. At its core, methane is a remarkably simple compound, just one atom of carbon linked to 4 atoms of hydrogen. It's the main component of the natural gas we might use to heat our homes, and here on Earth, it's absolutely everywhere, but its common nature belies its profound significance. You see, methane is what scientists call a biosignature, a substance that can serve as evidence, a potential clue for past or present life. And that's the key to understanding why its detection on Mars sends ripples of excitement through the scientific world. On our planet, the vast majority of methane has a biological origin. It's belched out by cows, released from decomposing plants in wetlands, and most intriguingly for Mars, produced by vast colonies of tiny microbes called methanogens. These microorganisms don't need oxygen to survive. They thrive in hidden, extreme environments like deep underground rocks, hydrothermal vents at the bottom of the ocean, or even within the frozen Arctic permafrost. They are life at its most tenacious, and they leave their unmistakable chemical calling card in the form of methane gas. So when we find methane in an alien atmosphere, our first, most thrilling thought is, could something like this be happening there too? However, and this is a crucial part of the mystery, methane can also be created without any biology at all. Geological processes like the interaction of certain rocks with water or the heat from volcanic activity can also produce methane in a process called serpentinization. It's a fascinating chemical reaction, but for an astrobiologist, it's the less exciting option. This creates a beautiful and frustrating scientific detective story. Is the methane on Mars a welcome mat from alien microbes? or is it just an interesting geological signpost pointing to active processes deep within the planet? Finding the answer is what makes this discovery so compelling. If the methane is biological, it would be arguably the most important discovery in human history, fundamentally altering our understanding of life's prevalence in the universe. But even if it turns out to be geological, it's still a huge deal. It would suggest that Mars is far from a dead planet. Its interior could still be warm and active, perhaps with liquid water interacting with its crust. And as we know from Earth, where there's liquid water and energy, life often finds a way. So either way, this simple molecule is pointing us toward something extraordinary happening on our neighboring world. This cosmic detective story began not on the surface of Mars, but from right here on Earth. The first tantalizing hints emerged in the early 2000s, when teams using powerful ground-based telescopes trained their instruments on the red planet. They were looking for the specific light signatures that molecules leave in the atmosphere, and to their astonishment, they found a faint but distinct fingerprint belonging to methane. It was a stunning announcement, but also a controversial one. The vast distance and our own atmosphere created a lot of noise in the data, leaving room for skepticism. Were we truly seeing a signal from Mars, or just an artifact from our own world? The plot thickened dramatically in 2004 with the arrival of the European Space Agency's Mars Express orbiter. Its instruments were designed to sniff the Martian atmosphere with far greater precision, and just a year after settling into orbit, it delivered. The probe confirmed the presence of methane, detecting a faint global background level of about 10 parts per billion. But more intriguingly, it also spotted occasional, larger plumes of the gas in specific regions, like the vast canyon system of Valles Marineris. This wasn't just a uniform haze, it was a gas that appeared, lingered for a short time, and then vanished. This behavior was as puzzling as the gas itself, because methane should theoretically stick around for centuries. Its rapid disappearance pointed to some unknown, highly efficient destructive process actively scrubbing it from the air. The mystery demanded a full-time detective on the ground, and that's exactly what NASA sent. When the Curiosity rover touched down in Gale Crater in 2012, it wasn't just a geological marvel, it was a mobile chemistry lab built for this very purpose. Its onboard instrument, called the Tunable Laser Spectrometer, or TLS, was designed to take deep, continuous breaths of the Martian air and analyze its composition. For its first year, Curiosity found nothing, adding a new layer of suspense. Then, in late 2013, it happened. The rover recorded a sudden, dramatic spike, a tenfold increase in atmospheric methane that lasted for several weeks before fading away. Since then, Curiosity has continued its patient watch, and it has documented these mysterious bursts multiple times. It has shown us that these events are seasonal, with concentrations peaking in the northern hemisphere's summer months, and that they happen suddenly, often at night. The rover has even been able to trace one particularly strong emission in 2019 to its probable source region right near its landing site. Each new measurement adds another crucial data point, transforming the mystery from a simple question of, "Is it there?" to the far more complex and thrilling puzzle of, "Why is it behaving like this?" These missions have given us the undeniable facts, setting the stage for the great debate that now consumes scientists worldwide. So with the stage set by those early orbital whispers, the real detective work began on the ground. Enter the Curiosity rover, our mechanical geologist and chemist, tirelessly exploring the vast, ancient basin of Gale Crater. Its most vital tool for this mystery is the sample analysis at Mars Instrument Suite, known as SAM. Think of SAM not as a single gadget, but as a complete portable laboratory, packed into a box about the size of a microwave oven. This incredible instrument is the heart of the mission's search for organic compounds and potential signs of habitability. It contains a gas chromatograph, a mass spectrometer, and the true star of our methane story, the tunable laser spectrometer or TLS. This laser spectrometer is an exceptionally precise nose. Here's how it works. Several times a month, as part of a carefully planned experiment, Curiosity's robotic arm will scoop up a soil sample, or, more importantly for gas detection, the rover will simply take a deep breath of the Martian air. This atmospheric sample is then filtered and fed into a small chamber inside the TLS. Once sealed inside, a carefully tuned laser is fired through the gas. Every molecule absorbs light in a unique way, like a signature barcode. Methane molecules are particularly greedy for a very specific wavelength of infrared light. By measuring how much of that specific light is absorbed, the TLS can count the number of methane molecules present with astonishing accuracy, detecting concentrations as low as 1/10 of 1 part per billion. That's like finding a single grain of sand in an Olympic-sized swimming pool. For its first Earth year on Mars, this sophisticated sniffer found nothing out of the ordinary. The background level of methane was so low it was virtually undetectable, a finding that was puzzling in itself. Then, in late 2013, the data plot suddenly jumped. The TLS recorded a breathtaking tenfold spike in methane, with levels soaring to around 7 parts per billion. This wasn't a gradual rise, it was a sudden, dramatic venting of gas that persisted for nearly 2 months before dissipating just as mysteriously as it appeared. The science team was astounded. They'd gone from a steady, boring flatline to a massive, undeniable pulse of gas. This pattern of quiet periods punctuated by sudden, short-lived bursts has become the defining characteristic of the Martian methane mystery. Curiosity has documented these events multiple times since that first discovery. Each event is like a sudden, faint exhalation from the planet itself. The data has even revealed a fascinating seasonal pattern, with these emissions peaking during the late northern summer on Mars. This seasonal rhythm is a massive clue, suggesting that whatever process is releasing the gas is tied to environmental factors, perhaps temperature changes or atmospheric pressure shifts that open and close subsurface pathways. Perhaps the most thrilling event came in 2019, when Curiosity detected its largest plume yet, a massive 21 parts per billion. The team was able to use atmospheric models and wind direction data to perform a cosmic backtracking exercise, tracing the likely origin of that particular puff of gas to a region just northwest of the rover's position. This was a monumental step. It moved the conversation from simply confirming the gas's presence to actively hunting for its source. These measurements from Gale Crater have given us the undeniable ground truth proof that the methane is real and that its behavior is bizarrely transient, setting the table for the great debate that now fuels so much scientific excitement. Is a geological process hiccuping this gas, or is it something far more profound? This erratic, spiking behavior is perhaps the most intriguing piece of the entire puzzle. On our own planet, when we see these sudden, temporary surges in methane, we immediately think of life. A marsh in the summer heat, for instance, doesn't release its methane at a constant, steady drip. As temperatures rise, the microbial communities within it become more active, fermenting organic material and releasing larger belches of gas in a process that's inherently tied to the seasons. The methane doesn't hang around for long. It's quickly consumed by other bacteria in the soil or broken down by chemical reactions in the atmosphere. So this pattern of brief, powerful peaks is a classic biological signature. Now, look at what Curiosity has found. The rover has recorded these sudden, dramatic increases in methane levels that appear seemingly out of nowhere, linger for a few weeks or months, and then vanish completely. The fact that these events aren't random but instead follow a discernible seasonal rhythm is a massive clue. The concentrations reliably peak during the late northern summer on Mars. This isn't a coincidence. It points to a process that is directly influenced by the Martian environment. Perhaps the subtle increase in temperature during the summer months is enough to thaw shallow subsurface ice, opening pores and cracks in the soil and allowing trapped gas to escape. Or maybe it triggers the metabolic activity of a subsurface biosphere, if one exists, causing them to become more active and release more of their waste gas, just like terrestrial microbes. A purely geological explanation has to work much harder to account for this specific pattern. A process like serpentinization, where water interacts with certain minerals like olivine to produce methane, is typically thought to be a slow, steady phenomenon, bubbling away at a constant rate deep underground. It shouldn't suddenly turn on and off with the seasons. For geology to be the culprit, we'd have to imagine a complex system where seasonal changes in surface temperature or atmospheric pressure somehow affect the deep subsurface, opening and closing valves on a geological scale, or where frost layers act as a temporary cap, trapping gas that is then released in a burst when the cap fails. While not impossible, it adds layers of complexity to the geological model, making the biological explanation appear, by comparison, elegantly simple. This is why the spiking pattern is so compelling to astrobiologists. It feels familiar. It matches a rhythm we understand from our own living world. Each sudden pulse detected by curiosity is like a faint, intermittent heartbeat, a potential sign that something on Mars is not just present, but active, breathing, and responding to its world in a way that feels hauntingly alive. It transforms the mystery from a static chemical detection into a dynamic, ongoing story, and it fuels the urgent desire to get closer to the source, to listen more intently, and to finally learn what or who is causing it. Of course, the scientific process demands we consider all possibilities, and there are compelling, entirely non-biological ways to explain this enigmatic gas. The leading geological suspect is a process known as serpentinization. Picture this: deep beneath the rusty surface of Mars, in the cold, dark bedrock, water, perhaps in the form of liquid brine that remains unfrozen despite the low temperatures, comes into contact with certain minerals rich in iron and magnesium like olivine. This interaction is a slow, ancient chemical dance. The water reacts with the rock, altering its structure, and as a byproduct of this transformation, releasing hydrogen gas. That hydrogen can then further react with carbon dioxide, which is plentiful in the Martian atmosphere and soil, to form methane and water. It's an elegant, entirely abiotic factory, producing the very gas we detect without a single microbe needing to be involved. This process is not just theoretical. We see it happening on Earth in places like the underwater Lost City hydrothermal field in the Atlantic Ocean, where great chimneys vent hydrogen and methane produced by similar rock-water reactions, creating oases of life that thrive on chemical energy rather than sunlight. Another plausible geological explanation points not deep underground, but to the surface itself. The Martian regolith, that layer of dust and soil that covers the planet, is constantly bombarded by ultraviolet radiation from the sun. We know that this soil contains a cocktail of organic compounds, carbon-based building blocks that have been delivered by meteorites over billions of years. This intense UV radiation acts like a powerful hammer, smashing apart these complex organic molecules in a process called photolysis. Just as sunlight can break down plastics here on Earth, it can break down these space-delivered organics on Mars, and one of the simple molecules that can be released from this destruction is, you guessed it, methane. It's a process that doesn't require any internal planetary activity at all. It's a surface-level phenomenon driven entirely by the sun's energy, slowly cooking the soil and releasing a faint, steady trickle of gas. Then there is the possibility of a frozen reservoir. Methane, under the right conditions of low temperature and high pressure, can become trapped within a cage of water ice molecules, forming what are known as clathrates or methane hydrates. On Earth, we find these strange, ice-like compounds deep under the ocean floor and in permafrost, and they store immense amounts of methane. Mars, with its cold climate and history of water, could easily have formed vast stores of these clathrates deep beneath its surface billions of years ago, perhaps from ancient biological activity that has long since gone extinct, or from even older geological processes. The intriguing idea is that these clathrates aren't necessarily stable forever. A shift in temperature from a change in climate, the heat from a meteorite impact, or even the slow geothermal warmth from the planet's interior could destabilize these icy cages, causing them to rupture and release their stored methane in sudden, powerful bursts. This could perfectly explain the sporadic, plume-like behavior Curiosity has observed, not a constant production, but a sudden, catastrophic release from a vast, ancient stockpile. Each of these geological theories presents a viable, lifeless pathway to the methane we see, reminding us that while the biological explanation is thrilling, the universe is full of complex chemistry that needs no life to create its wonders. To truly understand the mystery unfolding on Mars, it helps to look at the world right beneath our feet. Earth possesses a dynamic and complex methane cycle, a constant dance of creation and destruction that involves both biology and geology. Here, methane is a vibrant part of the carbon cycle. Vast communities of microbes known as methanogens are the planet's primary producers. They thrive in oxygen-free environments like the stomachs of ruminants, waterlogged rice paddies, and deep underground aquifers, consuming simple compounds and exhaling methane as a waste product. This biological engine is so potent that it generates the overwhelming majority of the methane in our atmosphere. But that's only half the story. Earth also has a powerful cleanup crew. Another class of microbes, called methanotrophs, literally consumes methane for breakfast. These bacteria live in soil and water, using the gas as their primary source of energy and carbon, effectively acting as a planetary biofilter that prevents methane from accumulating to extreme levels. This beautiful balance between production and consumption is a hallmark of a living, breathing world. Now, let's turn our gaze to Mars. The red planet presents a starkly different picture, one of profound silence and isolation. It's a frozen, arid world with a thin atmosphere that offers little protection from the sun's harsh ultraviolet radiation. Its surface is largely sterile, scoured clean by radiation and oxidizing compounds, making the existence of any surface-dwelling methanotroph seem incredibly unlikely. This lack of a destructive mechanism is actually a critical part of the puzzle. On Earth, methane has a lifetime of about a decade before it's broken down. But on Mars, without this biological cleanup crew, scientists initially calculated that any methane released should persist for centuries, slowly building up in the atmosphere to a much higher, more consistent concentration than what we actually observe. This is where the paradox deepens. The data from Curiosity doesn't show a steady, building background level. Instead, it reveals those sudden, short-lived spikes that vanish almost as quickly as they appear. This tells us that something on Mars is actively destroying the methane and destroying it with astonishing speed. So if it's not microbes consuming it, what is it? The leading theory points to the Martian soil itself. The surface is known to be rich in strong oxidants like perchlorates, chemicals that can break apart organic molecules. Scientists believe that when methane gas diffuses down and comes into contact with this toxic soil, it's likely being ripped apart through abiotic chemical reactions, potentially catalyzed by the relentless ultraviolet light that bathes the planet. This creates a fascinating contradiction. Mars might have a destructive process that is the complete opposite of Earth's, a harsh chemical scrubbing instead of a gentle biological recycling. This comparison between the two worlds illuminates the core of the mystery. If Mars had an active biological methane cycle like Earth's, we might expect to see a more stable background concentration with seasonal variations, not these erratic bursts. The very fact that the methane appears and disappears so rapidly argues for a powerful, non-biological destructive force at work on the surface, which in turn makes a biological origin for the gas itself seem less likely to some researchers. Yet the seasonal pattern of the releases echoes the biological rhythms we see on our own planet. This leaves us with a profound tug of war between two planetary stories. Is Mars a geologically active world where subsurface chemistry occasionally hiccups gas into an atmosphere that promptly tears it apart? Or are we witnessing the faint, struggling signature of a deep subsurface biosphere whose exhalations are quickly erased by the unforgiving chemistry of the surface? The tale of two planets shows us that the answer is not simple, and that the absence of Earth-like processes might be just as revealing as their presence. This rapid disappearance of methane adds another profound layer to the puzzle, creating what scientists call a source and sink problem. Think of the Martian atmosphere like a leaky bucket. The methane bursts Curiosity detects are the water being poured in, but the bucket never fills up because there's a massive hole in the bottom. That hole represents the destructive, or sink, processes actively scrubbing the gas from the air. For us to see any methane at all, the rate at which it's being poured in must, at times, significantly outpace the rate at which it's draining out. The fact that we consistently see these sudden pulses means the source isn't just a one-time event. It has to be ongoing and robust enough to momentarily overwhelm an incredibly efficient destructive system. So what is creating this massive hole in the bucket? The prime suspect is the relentless, unfiltered ultraviolet radiation from the sun. Mars, lacking a protective ozone layer like Earth's, is bombarded by this high-energy light. When UV photons strike methane molecules in the thin atmosphere, they act like tiny wrecking balls, breaking the bonds that hold the carbon and hydrogen atoms together. This shattering initiates a complex cascade of photochemical reactions. The broken pieces, known as radicals, are highly reactive and quickly combine with other compounds in the air, ultimately forming carbon dioxide and water vapor. This process is brutally efficient. Based on the known chemistry, models suggest that any methane released into the Martian atmosphere should be completely broken down within just 300 to 600 years, a geological blink of an eye. This creates a staggering temporal paradox. If the methane we're seeing today is just a temporary spike, it implies the releasing event must have happened very, very recently. But if the methane is being produced by slow, deep geological processes like serpentinization, it's difficult to imagine how it could be released in such sudden, violent bursts that coincide with the modern Martian seasons. This timing problem is what makes the potential for a biological source so tantalizing to many researchers. An active subsurface microbial community could, in theory, respond to seasonal changes in temperature or pressure by modulating its metabolic activity, turning the production of methane up and down like a faucet, thereby directly creating the observed pattern of brief, powerful releases that punch through the atmosphere's destructive cycle before being swiftly erased. Pinpointing the exact origin of these enigmatic methane puffs is arguably the greatest planetary detective story of our time, and it's a task that pushes our current technology to its absolute limits. Imagine trying to find a single, intermittently active gas vent somewhere on an entire planet that's as vast and varied as all of Earth's continents combined, using only a handful of robotic sentinels that are millions of miles away. The Curiosity rover, for all its incredible capabilities, is like a lone weather station in the middle of a massive desert. It can tell us when the wind blows and detect a strange smell on the breeze, but it can't see the distant campfire that might be causing it. Its measurements are incredibly local, confined to the single crater it calls home. To truly hunt the source, scientists need to think like atmospheric detectives. When Curiosity detects a spike, the team immediately gets to work on a process called backtracking. They take a snapshot of the atmospheric conditions at that exact moment: wind speed, wind direction, temperature, and pressure. Then they run sophisticated computer models that essentially play the video of the atmosphere in reverse, tracing the path of that methane plume backward through time and space to estimate where it might have originated. This is how they were able to point to a region northwest of Gale Crater following that large 2019 plume. It's a brilliant piece of scientific deduction, but it's still just an educated guess, a probability circle on a map that could be dozens of miles across. To confirm it, you'd need to be there on the ground in that exact spot, at the exact moment the gas is being released. This is where orbital assets come into play, acting as our eyes in the sky. The ExoMars Trace Gas Orbiter, a joint mission between the European and Russian space agencies, was specifically designed for this hunt. Its primary goal was to map the distribution of methane across the entire planet with sensitivity 100 times greater than previous instruments. The puzzling twist: for the most part, it has found nothing. It has detected no significant methane plumes in the atmosphere, which seems to directly contradict the ground-level findings from Curiosity. This discrepancy isn't a failure, it's a massive clue. It suggests that the methane releases are not only transient but also incredibly localized and confined to the very lowest layer of the atmosphere, perhaps just a few meters above the surface. The gas might disperse and break up so quickly that by the time it rises high enough for an orbiter to see it, it's already gone. This means our orbital scouts might be flying too high to see the brief, faint whispers of gas that the rover on the ground can smell. This immense challenge informs every aspect of future mission planning. The next generation of rovers, like the recently deployed Perseverance, carry enhanced instrumentation, but their strategy is also evolving. Rather than waiting to stumble upon a source, the long-term plan involves a multi-platform approach, a network of assets working in concert. Imagine a future where multiple rovers act as ground-level sniffers, communicating with each other, and with a new fleet of orbiters equipped with sensors specifically tuned to detect these low-altitude, short-lived plumes. Even more promising are proposed missions that would include a Martian helicopter, far more advanced than Ingenuity, capable of flying from a rover's location directly to a suspected vent site to sample the air right at the source. Cracking this case won't come from a single eureka moment, but from a patient, global, coordinated effort to finally corner the mystery and see, with our own eyes, what is breathing beneath the rusty soil of Mars. This hunt for a smoking gun on Mars feels like a modern quest, but to truly appreciate how far we've come, we have to rewind the clock nearly half a century to the very first time we seriously went looking for life on the Red Planet. The Viking program of the 1970s was a monumental leap of faith and technology. It wasn't just about landing on Mars, it was about conducting the most sophisticated biological experiments ever attempted off-world. The two Viking landers were equipped with a suite of instruments, but one in particular has become the stuff of legend and fierce debate: the Labeled Release Experiment, or LR. Its design was beautifully simple and brilliant. Each lander extended its robotic arm, scooped up a small sample of the rusty Martian soil, and deposited it into a tiny test chamber on board. Then a nutrient soup, a carefully crafted cocktail of organic compounds that any Earth microbe would find delicious, was injected into the sample. But this wasn't just any food. The nutrients were labeled with a radioactive carbon isotope. The idea was straightforward. If there were any microorganisms in that soil metabolizing the nutrients, they would consume the soup and, as a natural byproduct of their digestion, release waste gas. And because that waste gas would contain the radioactive carbon, a simple detector would spot it, signaling a triumphant discovery of life. To the astonishment of the scientists watching from millions of miles away, that's exactly what seemed to happen. In both Viking 1 and Viking 2's experiments, when the nutrient was added, the sensors immediately detected a significant release of radioactive gas. It was a pulse, a signal that looked for all the world like the metabolic activity of living organisms. The initial excitement was electric. Had we just, on our first attempt, found evidence of life on another planet? But that excitement was short-lived. The triumph quickly curdled into profound ambiguity because of another Viking experiment, the gas chromatograph mass spectrometer, which was designed to directly sniff the soil for complex organic molecules, the very building blocks of life, found nothing. Not a trace. It was as if you'd walked into a bustling kitchen. You could smell a freshly baked pie, but when you looked in the oven, it was completely empty and cold. This contradiction was baffling. How could there be a biological response without any biological material present? The scientific consensus eventually settled on a non-biological explanation. The prevailing theory became that the Martian soil was not teeming with life, but was instead packed with powerful, super-oxidizing chemicals like perchlorates. These harsh compounds, constantly activated by the sun's intense ultraviolet light, could have reacted with the nutrient soup itself, breaking it down abiotically and releasing the radioactive gas in a mimicry of life. The official conclusion was that the LR had detected interesting but non-biological chemistry. For decades, that was the end of the story. Mars was declared a dead world. But the modern detection of methane has forced a dramatic and compelling reassessment of those old Viking results. The two mysteries are now deeply intertwined. Those of us who look back see a stunning parallel. The labeled release experiment detected a transient gaseous signal that appeared when a nutrient was added and then, in later control tests, seemed to disappear. Curiosity is now detecting transient gaseous methane signals that appear and then mysteriously vanish. The modern debate between a biological or geological source for methane is a direct echo of the Viking debate. What if the Viking landers did find life, but we simply didn't have the context or the technology to recognize it for what it was? Some scientists have powerfully argued that the superoxidants once used to dismiss the LR results could actually be part of the story. If Martian microbes exist, they would likely live not on the deadly, irradiated surface but safely underground. Their metabolic waste, perhaps methane or another organic gas, could slowly diffuse upward. When it reached the surface, it would be immediately destroyed by those same oxidants, leaving behind no trace of the complex organics the Viking instrument was built to find, yet potentially creating the chemical conditions that caused the false positive. The Viking landers may have been right all along, but their discovery was just too far ahead of its time. A ghostly whisper we are only now, with our modern rovers and our methane mystery, finally learning how to hear. So, with curiosity providing ground truth evidence of these mysterious methane bursts, the next logical step was to get a much broader view from orbit. This led to one of the most anticipated arrivals at the Red Planet in recent memory, the ExoMars Trace Gas Orbiter, a flagship mission from the European Space Agency and Roscosmos. This spacecraft was in many ways custom-built to solve this very puzzle. Its name says it all. Its primary mission was to conduct a precise, planet-wide census of trace gases, with methane being public enemy number one. The scientific community held its breath, expecting this powerful new eye in the sky to finally map the methane plumes, pinpoint their sources, and perhaps even hand us the answer to the mystery on a silver platter. The orbiter's instruments represented a staggering leap in technology. Its two key tools were a harmony of precision. The first, called NOMAD, which stands for Nadir and occultation for Mars discovery, is a supremely sensitive spectrometer. It works by analyzing sunlight that has filtered through the Martian atmosphere, looking for the unique fingerprints of molecules within that light. The second instrument, the atmospheric chemistry suite, performs a similar function with even more complementary techniques. Together, they were designed to detect methane at concentrations as low as 50 parts per trillion. That's a level of sensitivity that should be able to smell a single methane molecule hiding among billions of others from hundreds of miles away. If there was methane consistently in the atmosphere, this orbiter would find it. The results, however, were not just surprising, they were profoundly confounding. After meticulously scanning the atmosphere for years, the ExoMars orbiter has, for the most part, found nothing, no large plumes, no significant background levels. Its data paints a picture of a Martian atmosphere that is, for all intents and purposes, completely devoid of the methane that Curiosity keeps sniffing out down below. This isn't just a minor discrepancy, it's a massive contradiction that sent scientists back to the drawing board. How could our most sensitive orbital sniffer detect absolutely nothing, while our rover on the ground regularly measures significant localized bursts? It felt like two detectives investigating the same crime scene were coming back with completely irreconcilable stories. This puzzling contradiction, however, is far from a failure. In science, a null result is still a result, and this one has become one of the most crucial clues in the entire investigation. It has forced researchers to develop a new and compelling theory about the behavior of methane on Mars. The leading hypothesis now is that the methane releases are not only transient but also incredibly localized and confined to the very lowest layer of the atmosphere, what's called the planetary boundary layer. This is the air that is literally right at the ground level, perhaps just a few meters or tens of meters thick. The idea is that the methane is being released in these brief, powerful puffs, maybe from a specific crack in a rock or a small vent, and it doesn't linger or rise. It's almost immediately destroyed or diluted by the time it mixes into the higher atmosphere where the orbiter is looking. The destructive processes on the surface, those harsh oxidants and UV radiation, are so efficient that they act like a planetary-scale disinfectant, scrubbing the gas away before it can ever become a widespread, detectable feature from orbit. This means the ExoMars Trace Gas Orbiter and the Curiosity rover aren't actually contradicting each other. They are telling two different, complementary parts of a much more complex story. Curiosity is our ground-level witness, perfectly positioned to catch the brief, local crime as it happens. The orbiter is our high-altitude surveillance satellite, confirming that whatever is happening down there isn't starting a planet-wide phenomenon. This interpretation completely reshapes our understanding of the methane cycle on Mars. It suggests that the source of the gas must be hyper-localized and that the sink, the destructive process, is unbelievably fast and efficient. The mystery has deepened, but in a way that brings us closer to the truth, forcing a more nuanced and sophisticated search for answers that continues with every new pass of the orbiter and every new breath taken by the rover. This apparent contradiction between our ground observer and our orbital sentinel isn't a scientific failure. It's a massive, flashing clue that is forcing us to completely rethink how methane behaves on the red planet. The leading theory that has emerged to explain this baffling discrepancy is as elegant as it is frustrating for would-be detectives. Scientists now believe that the methane releases on Mars are not only transient but also incredibly localized and confined to the very lowest layer of the atmosphere, a thin blanket of air just meters above the ground known as the planetary boundary layer. Imagine a single geyser occasionally spouting a brief, faint mist. Curiosity is the lucky observer standing right next to it, getting lightly dampened by the spray. The Trace Gas Orbiter, meanwhile, is like a satellite high in the sky, looking down at the entire valley. By the time that mist from the geyser even begins to rise and disperse, it has already vanished, completely invisible from a global perspective. This isn't a case of one instrument being wrong. It's a case of each instrument seeing a different part of a much more complex and rapid process. The key to this theory lies in the brutal Martian surface environment. We've long known that the Martian soil is rich in powerful oxidizing compounds like perchlorates, which are essentially cosmic bleach, activated by the relentless barrage of ultraviolet radiation from the sun. The new thinking is that this harsh chemical soup doesn't just sit there passively. When a tiny, localized puff of methane is released from a crack or a vent, it doesn't have a chance to accumulate and rise. Instead, it immediately comes into contact with these surface oxidants and is torn apart in a violent, abiotic chemical reaction. This destruction is so swift and so efficient that it acts like an invisible firebreak, preventing the gas from ever building up into a large, detectable plume that could drift high into the atmosphere for the orbiter to see. The methane is essentially being scrubbed from the air almost the instant it appears, creating a "now you see it, now you don't" phenomenon that only a ground-based instrument with a front-row seat can reliably catch. This explanation also helps solve another part of the puzzle: the mysterious seasonal variation curiosity has observed. The efficiency of this surface destruction mechanism is likely tied to environmental factors like temperature and humidity. During the warmer Martian summer months, the thin layer of water frost on soil particles might sublimate away, changing the chemical reactivity of the surface layer and perhaps making it slightly less efficient at destroying methane for a brief window. Alternatively, the increased warmth could slightly increase the pressure of subsurface gas, allowing for stronger, more sustained releases that momentarily overpower the destructive capacity of the soil, leading to the observed spikes. This creates a beautiful, if complex, feedback loop where the release and destruction of methane are in a constant, delicate dance dictated by the Martian seasons. The data from Curiosity and the silence from the trace gas orbiter are no longer a contradiction. They are the two essential data points that, when viewed together, reveal a planetary process far more dynamic and fascinating than anyone could have imagined. This brings us to a pivotal and humbling reality in the search for life. The detection of methane while electrifying is not a smoking gun. It is what scientists call a potential biosignature, a clue that whispers of possibility rather than a verdict that shouts of certainty. On our own planet, methane is so thoroughly intertwined with biology that its presence elsewhere immediately sets our imaginations racing. But the universe is a master chemist capable of crafting the same molecules through vastly different recipes, some that involve life and many that do not. A potential biosignature is not proof. It is the starting pistol for a rigorous process of elimination, a cosmic trial where we must act as both prosecutor and defense attorney, methodically arguing against our own most hopeful conclusions. The true weight of evidence comes not from a single gas but from the context in which we find it. Imagine you're a detective and you find a fingerprint at a crime scene. That fingerprint is a clue, a potential link to a suspect, but you wouldn't arrest someone based on that alone. You'd need to know if they had an alibi, if their print matched the one on file, and if there was other evidence like eyewitnesses or a motive to place them there. Methane is that fingerprint. Its presence makes us look up, but to truly accuse the universe of harboring life, we need the full context. We need to understand the other gases swirling around it. This is where the concept of specificity becomes everything. Life doesn't just produce methane in a vacuum. It operates within a complex web of chemical processes. On Earth, biological methane is often accompanied by other gases that serve as supporting evidence. For instance, microbes that produce methane might also produce ethane or other complex hydrocarbons. Or the very process of life might create an imbalance in the ratios of different carbon isotopes. Methane from biological sources tends to be slightly richer in the lighter carbon-12 isotope, as life finds it easier to use than the heavier carbon-13. Finding methane alongside these specific companions, a particular suite of other gases, or a specific isotopic signature, would be like finding that fingerprint alongside a matching shoe print and a confirmed eyewitness. It would build a much stronger, more compelling case. Our current dilemma on Mars is that we have the fingerprint, but we're still searching for that corroborating evidence. The instruments on Curiosity are magnificent, but they have their limits. They can tell us the methane is there and even hint at its isotopic composition, but to get the full picture, we need more. We need to be able to detect vanishingly small amounts of other gases that might be hiding in the Martian air. We need to understand the geological context of the release site. Is it an area with ancient clays that could have hosted life, or is it near volcanic features that could hint at subsurface heating? Most importantly, we must relentlessly pursue and rule out every single conceivable non-biological explanation. We have to prove that the methane couldn't have been made by serpentinization or UV degradation of meteoritic organics before we can seriously entertain that it was made by microbes. This is the scientific process at its most strict and most beautiful, a disciplined, evidence-based march toward the truth, where extraordinary claims require not just extraordinary evidence, but a complete absence of any other viable explanation. The journey to confirm life is a marathon of elimination, and we are still running the first few miles. This is precisely why the search for life is never about a single magical bullet. Finding methane is like hearing a single, intriguing note from a vast and complex symphony. To understand the music, we need to hear the entire orchestra. Scientists approach this detective work holistically, knowing that a true biosignature is rarely a lone gas, but rather a chorus of clues singing in harmony. The presence of methane opens the door, but to step through it with confidence, we must look for the other players in the ensemble that would make a biological origin the most compelling explanation. One of the most critical supporting actors in this cosmic drama is the presence of complex organic molecules. Methane itself is a very simple organic compound, but life as we know it builds far more intricate structures: the proteins, lipids, and genetic material that form the machinery of a cell. Finding these larger, more complex organics alongside methane would be a game changer. It would be the difference between finding a single, basic Lego brick and finding an entire, partially assembled Lego model. The brick could have arrived in any number of ways, but the model strongly suggests a builder. The Curiosity rover has indeed detected a variety of organic molecules in Martian rocks, but they tend to be simple, like benzene or propane. The tantalizing next step is to find truly complex chains, the kind that are notoriously difficult to form without biological assistance, existing in the same place and at the same time as a methane release. That correlation would be a powerful piece of evidence. Beyond the chemicals themselves, the geological context of where these signals are found is equally vital. You wouldn't expect to find a thriving coral reef in the middle of a desert. You'd look for it in warm, shallow, sunlit waters. Similarly, astrobiologists are intensely focused on specific mineralogical and environmental settings on Mars that are known to be friendly to life. The most promising of these are ancient clay-rich rocks, particularly smectites. These clay minerals form in the presence of neutral pH water, and they have a fantastic property. They are excellent at trapping and preserving organic matter, protecting it from radiation and oxidation for billions of years. If we were to detect a steady methane seep emanating from a layer of these ancient habitable clays, the biological explanation would instantly become far more plausible than if the gas were coming from a volcanic basalt plain. The location of the clue tells its own story, and of course, underpinning all of this is the eternal prerequisite: liquid water. Life as we understand it is utterly dependent on water as a solvent for its biochemical reactions. The mantra, "Follow the water," has driven Mars exploration for decades, and we now know the planet was once awash with rivers, lakes, and even a vast northern ocean. The question is whether any of that water remains liquid today. Evidence points to possible briny aquifers deep underground and even transient liquid water at the surface, but confirming a present-day, stable reservoir would be monumental. A methane source linked to a confirmed subsurface lake, like those suspected under the South Pole, would create an incredibly compelling narrative. It would sketch a picture of a potential isolated aquatic habitat, cut off from the harsh surface, where microbes could potentially metabolize and produce gas that slowly leaks up to the world above. Each of these clues, the complex organics, the hospitable minerals, the liquid water, doesn't stand alone. Their power is in their convergence. A methane detection becomes exponentially more exciting when it occurs in a place that has all the other right conditions for life to not just exist but to potentially thrive. Given the brutal conditions on the surface, it seems almost certain that if life exists on Mars today, it isn't sunbathing on the rusty plains. Instead, the most promising real estate for any modern Martian microbe would be deep underground, in what scientists call the subsurface habitable zone. Picture this: just a few meters beneath your feet, the entire character of the planet changes. The relentless, DNA-shredding ultraviolet radiation from the sun is completely blocked out by tons of overlying rock and soil. The wild temperature swings that see the surface plummet to -100 degrees Celsius at night are dampened into a stable, consistently cold but far more manageable climate. It's a dark, quiet, and protected world, and it may be the last refuge for life on Mars, but a safe haven isn't enough. Life also needs a cocktail of key ingredients to survive. This is where another fascinating possibility emerges: briny aquifers. We know that pure liquid water would freeze instantly on the surface, but water laden with dissolved salts known as brine has a much lower freezing point. Scientists believe that vast reservoirs of this salty, supercooled liquid could be pooled deep within porous rocks beneath the Martian South Pole and elsewhere. Data from orbital radar instruments has even detected what appear to be signs of these subsurface lakes, buried under a mile of ice. These wouldn't be clear, bubbling springs. They'd be dark, cold, hypersaline environments, perhaps similar to the liquid brine lakes found deep beneath the Antarctic ice sheets on Earth. And as we've discovered in those extreme places on our own planet where there is liquid water, even incredibly salty water, and a source of energy, life finds a way. So what would these Martian microbes actually eat? Without sunlight for photosynthesis, they would have to rely on another power source: chemistry. This is a process we call chemosynthesis. Imagine vast colonies of microorganisms, not unlike the methanogens we have on Earth, surviving on a diet of basic inorganic chemicals. Their food source could be the hydrogen gas produced naturally deep underground through the serpentinization process, where water reacts with certain minerals like olivine. Or they might metabolize the carbon dioxide that permeates the Martian soil, or even the simple organic compounds delivered by billions of years of falling meteorites. They would use this chemical energy not to grow and thrive in a bustling ecosystem, but likely to simply persist to repair their cells and maintain a slow, steady metabolic existence in a state of near hibernation, perhaps for millennia at a time. And their waste product from this quiet chemical existence, methane. For a methanogen, producing methane is a fundamental part of its energy-generating process. A deep subsurface biosphere, isolated in these dark, watery pockets, could be slowly but steadily producing this gas as a byproduct of its metabolism. This gas wouldn't just stay down there, it would slowly diffuse upwards through cracks and pores in the rock, seeking a path to the lower pressure of the atmosphere. Some of it might get trapped in other mineral formations or frozen into clathrates, but some of it would eventually find its way to the surface, venting out in those brief, localized puffs that curiosity detects. The seasonal pattern of these releases could be explained by the subtle changes in surface temperature. The slight warmth of the Martian summer could be enough to shift the pressure ever so slightly in these underground systems, or to thaw minute icy caps on vents, acting like a valve that allows built-up gas to escape in a seasonal exhale. This theory paints a picture of a planet that is not dead, but quietly, slowly breathing a world with a hidden, tenacious pulse that we are only just beginning to sense. To grasp why this subterranean world is even a possibility, we have to journey back in time, not just a few million years, but billions. The Mars we see today, a frozen, arid desert under a thin, pink sky, is a ghost of its former self. The evidence gathered by our orbiters and rovers paints an undeniable and breathtaking picture. Ancient Mars was a profoundly different planet. It was a world adorned with vast, flowing rivers that carved canyons deeper than any on Earth, with deltas that emptied into shimmering lakes, and perhaps even a great ocean that dominated its northern hemisphere. This wasn't a dead world. It was a dynamic, water-rich environment, strikingly similar to the early Earth at the very time when life first took hold on our own planet. This transformation was made possible by a key ingredient that Mars tragically lost: a robust magnetic field. In its youth, Mars likely had a churning, molten core that generated a protective magnetic shield, much like Earth's does today. This shield deflected the onslaught of the solar wind, the constant stream of charged particles pouring from the Sun. With this protection in place, Mars could maintain a thick, warm atmosphere. This atmosphere created a greenhouse effect, trapping heat and allowing liquid water to persist on the surface for perhaps 1 billion years or more. That is an immense stretch of geological time, more than enough for the simple chemistry of a primordial soup to stumble into the miraculous complexity of biology, just as it did in Earth's ancient seas. This idea of a habitable ancient Mars is not just speculation. We have the geological scars and sediments to prove it. The Curiosity rover has been driving through what was once the bed of a large lake in Gale Crater. It has drilled into layered mudstones, rocks that can only form at the bottom of still, long-lasting bodies of water. These rocks are rich in clay minerals like smectite, which are themselves formed by the interaction of neutral, life-friendly water with volcanic rock. Elsewhere from orbit, we see the unmistakable patterns of ancient river deltas, alluvial fans, and shorelines etched permanently into the landscape. These features tell a silent, powerful story of a world that was once alive with the cycle of water, evaporation, rain, flow, and collection. This is where the methane mystery connects to the deep past. If life did emerge during this clement era, it would have found a world of immense opportunity. Microbes could have thrived in those surface lakes and rivers. But as Mars's fate turned, so too would the fate of any nascent biosphere. When the planet's core cooled and its magnetic field failed, the solar wind was allowed to strip away the atmosphere, molecule by molecule, over millions of years. The air pressure dropped, the temperatures plunged, and the surface waters either evaporated into space or froze solid, locking away the remnants of that warmer age in immense ice caps and deep permafrost. The surface became a radioactive desert, a place utterly inhospitable to life as we know it. But life is tenacious. It doesn't simply give up, it retreats. Any surviving microbes would have been forced to follow the water down, seeking refuge in the only place that remained viable, the subsurface. They would have migrated deeper into the porous aquifers, into the damp cracks between rocks, and into the dark, protected realms where liquid brine might still persist. There, isolated from the dying surface, a subsurface biosphere could have hunkered down, entering a state of ultra-slow metabolic maintenance, a billions-year-long hibernation. Their existence would be a whisper, not a shout. They wouldn't be building civilizations, they would simply be persisting, their metabolism reduced to a barely tickling pulse, perhaps producing methane as a waste product in these isolated, chemical-driven ecosystems. This grand narrative offers a profound and elegant explanation for the methane we detect today. The gas Curiosity sniffs in sudden bursts could be the faint, lingering breath of a biosphere that flourished when Mars was young. It is the metabolic exhaust from organisms that first awakened in a world of rivers and lakes, and that now slumber deep beneath the frozen soil, their ancient biological processes still occasionally venting gas that rises to remind us of their possible existence. The methane becomes more than a molecule. It becomes a fossil, not locked in stone, but a gaseous relic of a lost world, a last echo from a time when two planets in our solar system might have both buzzed with the quiet hum of life. This is where the investigation truly enters its most thrilling phase, moving from remote sensing and robotic analysis to the realm of tangible, physical proof. For all their sophistication, the instruments we can send to Mars on a rover are, by necessity, miniature marvels of engineering incredibly capable, but still a fraction of the size and power of the vast laboratories we have here on Earth. They are like a detective working a crime scene with only a magnifying glass and a field test kit. They can find clues and make strong inferences, but to get a conviction, you need to send the evidence back to the full forensic lab for DNA sequencing, electron microscopy, and every other tool at your disposal. This is the monumental ambition of NASA's Mars Sample Return Campaign, a multi-mission endeavor that represents the next great leap in planetary science and the single best chance we have to finally solve the methane mystery and the question of life itself. The campaign is already underway. The Perseverance rover, which landed in Jezero crater in 2021, is not just exploring, it is a mobile, robotic geologist on a curated sample collection mission. Its sole purpose is to seek out the most promising rocks and soil, those from an ancient river delta environment that once flowed into a lake, a place perfectly suited to have preserved signs of ancient life. It carefully drills core samples, seals them in ultra-clean tubes, and leaves them in carefully documented caches on the surface, creating a treasure map of the most scientifically valuable material on another planet. These aren't just random rocks, they are a carefully chosen library of Martian history, selected specifically to answer the questions we've been asking for decades. The next steps are where the mission moves from ambitious to almost unbelievable in its complexity. Later this decade, NASA and the European Space Agency plan to send a second mission to the Red Planet. This lander will be a dedicated fetch vehicle, touching down near the cache site and deploying a small helicopter or a second rover to swiftly go out, gather the sample tubes and bring them back to the lander. There, a small, sturdy rocket called the Mars Ascent Vehicle will be waiting. This vehicle will perform a historic first, launching from the surface of Mars with the precious cargo sealed inside a protective orb. Once in Martian orbit, this container will be met by a waiting European-built spacecraft which will carefully capture it, secure it within a multi-layered biocontained system, and begin the long journey back to Earth. The analysis that will then be possible is simply beyond anything we can currently achieve. In labs equipped with instruments the size of rooms, scientists will be able to slice the samples into layers thinner than a human hair, searching for microscopic textures and patterns that could only have been formed by biological processes, what we call biosignatures. They will be able to perform ultra-precise isotopic analysis, measuring the ratios of carbon, hydrogen, and other elements with an accuracy that could definitively distinguish between a biological and a geological origin for any organic matter, including methane precursors trapped within the rocks. Most powerfully, they could potentially find fossilized evidence of the microbes themselves, preserved in the fine-grained mudstones of an ancient lakebed. The stakes for this endeavor could not be higher. Bringing Martian material to Earth is the only way to conduct the kind of open-ended, iterative, and globally collaborative science that a discovery of this magnitude demands. It allows for hypothesis testing that remote robots simply cannot perform, where one experiment leads to a new question, which leads to a new analytical technique in a continuous cycle of discovery. A positive result would not just be a data point on a graph. It would be a physical specimen that we could hold, study, and point to as proof that we are not alone in the universe. The Mars Sample Return Campaign is our generation's moonshot, a daring and technically breathtaking effort to bring a piece of another world home, and in doing so, perhaps finally read the story written in its stones. And so the torch of exploration is passed to a new generation of robotic pioneers, with NASA, a Perseverance rover, leading the charge into this bold new era of investigation. Touching down in the breathtaking Jezero crater in 2021, Perseverance represents a fundamental shift in strategy from its predecessor, Curiosity. While curiosity was our chemist sniffing the air and analyzing drilled powder on the spot, Perseverance is our archivist, a mobile field geologist with a primary mission to collect and cache the most promising samples for eventual return to Earth. Its landing site was chosen with exquisite care. Jezero is not just another crater, it's the fossilized remnant of an ancient river delta where a waterway once emptied into a vast lake. This is precisely the kind of environment we know from Earth is exceptional at preserving the biosignatures of past life, trapping and protecting organic material in its fine-grained sediments for billions of years. Although Perseverance doesn't carry a dedicated methane sniffer like Curiosity's TLS, its contribution to solving the overarching mystery of life on Mars is absolutely pivotal. Its suite of instruments, named with the delightful acronym SHERLOC, is designed to perform a different kind of detective work. It uses cameras and ultraviolet lasers to map the microscopic texture and chemical composition of rocks in extraordinary detail, searching for those subtle patterns and mineral associations that could only have been formed by biological processes. It's looking for the literal fossils of ancient microbial mats or the chemical ghosts of their cell walls, evidence that would be impossible to definitively confirm with remote instruments alone. By characterizing the habitability of this ancient environment down to the microscopic scale, Perseverance provides the essential context. If we were to one day confirm a biological source for the methane, understanding the ancient habitable world those microbes might have evolved in would be the key to the entire story. The rover's most visible task, however, is its sample collection. Using a sophisticated drill at the end of its robotic arm, Perseverance cores pristine rock samples, seals them in ultra-clean titanium tubes, and carefully deposits them on the surface in strategic caches. This act is more than just collecting rocks. It is laying the groundwork for perhaps the most complex robotic space mission ever attempted, Mars sample return. These tubes represent our best chance to finally get our hands on the evidence, to bring pieces of Mars back to laboratories on Earth where we can subject them to analysis far more precise and comprehensive than any rover-bound instrument could ever manage. We could search for those complex organic molecules, perform definitive isotopic analyses on any trapped gases, and even look for microscopic fossil structures, the kind of proof that would settle the debate once and for all. Perseverance's work therefore creates a powerful bridge between the present-day atmospheric mystery and the planet's deep past, while Curiosity monitors the potential breathing of a modern Martian biosphere. Perseverance is busy excavating the geological tomb of an ancient one. The two missions are not in competition, they are complementary chapters in the same epic investigation. The methane detected today could be the faint echo of the very life forms whose fossilized remains Perseverance is now collecting. By understanding the conditions that made Jezero Crater a potential cradle for life billions of years ago, we gain a critical framework for interpreting the tantalizing, enigmatic signals we're detecting in the modern atmosphere. This multi-generational, multi-mission approach shows just how seriously we are taking this quest, deploying every tool at our disposal to answer the profound question of whether life has ever existed, or perhaps still exists on the world next door. But for all their incredible capabilities, our robotic explorers on Mars are fundamentally limited. They move with painstaking slowness, their actions planned days in advance by teams millions of miles away. They can only drill a few inches into the rock, and their ability to react to unexpected discoveries is constrained by their programming. To truly crack this case wide open, we need to put the ultimate tool on the ground, the human mind. Imagine a team of astronaut geologists, their boots planted firmly in the red dust, their own eyes scanning the horizon for the subtle clues that no rover camera could ever prioritize. This is where the search could transition from a slow, methodical crawl into a dynamic, intuitive hunt. A human explorer brings something no machine can replicate: instant synthetic intuition. A rover might spend weeks analyzing a single rock formation, but a trained geologist could glance at a hillside and immediately recognize the telltale signs of a past groundwater seep or a mineral deposit associated with methane-producing reactions on Earth. They could see a strange color in the soil, a peculiar fracture in a boulder, or a faint wisp of dust caught in a certain way by the wind and think, "That looks interesting, let's go check that out right now." This ability to make on-the-spot connections, to follow a hunch based on years of experience, would be utterly revolutionary. They wouldn't just follow a preset path, they would truly explore, turning the entire landscape into an active crime scene to be investigated in real time. This human flexibility would be most powerfully applied to the methane mystery itself. Picture a scenario where an orbiting satellite detects a faint, transient methane plume emanating from a rugged canyon system. Alerted to the event, a crew living at a nearby base could be in their pressurized rover and heading toward the source within hours. As they approach, they might use handheld sensors to map the gas concentration in the air, literally following the scent like bloodhounds to pinpoint the exact fissure or vent from which the gas is escaping. They could then get out, kneel down, and examine the vent site up close, collecting the right samples from the exact right place with a delicate precision no robotic arm can match. They could tap the rock with a hammer, feeling its texture and listening to its sound, gathering immediate tactile data that would take a rover days to infer. And then comes the most critical step, drilling. Our current rovers can only scratch the surface, both literally and figuratively. A human mission would bring a powerful drill rig capable of boring dozens, even hundreds of meters down, deep into the hypothesized subsurface habitable zone. They could core directly below a methane vent, retrieving pristine samples of the soil layers, any potential briny aquifers, and even the microbial life we suspect might be there. If they hit a pocket of gas or liquid, they would know instantly and could adjust their technique on the fly to contain and sample it without contamination. They wouldn't have to wait months for commands from Earth. They could solve problems in the moment, ensuring the integrity of the most precious samples imaginable. The presence of humans would turn a decade-long robotic campaign into a mission of perhaps a single, electrifying afternoon. The combination of human intuition, real-time problem-solving, and powerful tools could allow us to move from detecting a mysterious atmospheric gas to holding the source of that gas in our hands within a single Martian day. It would be the culmination of centuries of wondering, decades of robotic reconnaissance, and years of meticulous planning, all leading to a moment where a human being on another world finally uncovers the answer to one of humanity's oldest questions. Confirming the existence of life on Mars, even in the form of a single, humble microbe, would be far more than a scientific headline. It would be a tectonic shift in human consciousness, a moment that fundamentally recalibrates our understanding of reality itself. For all of human history, our planet has been the solitary, cherished example of a living world, a biological oasis in a cosmic desert we perceived as vast and empty. This discovery would shatter that isolation forever, transforming the universe from a silent, sterile expanse into a place that is potentially humming with biology. The philosophical implications are staggering. It would force us to confront the profound question of whether life is a miraculous, incredibly rare fluke, or if it is instead a cosmic imperative, a natural and common outcome wherever the right conditions persist. Are we a statistical anomaly, a one in a trillion accident, or are we simply part of a grand galactic ecosystem? The answer would redefine our very identity. This revelation would send shockwaves through every system of belief, challenging centuries of theological and philosophical thought. Many faith traditions would likely find ways to incorporate this new reality, seeing it as a testament to the boundless creativity of a divine creator, a universe filled with even more wonder and diversity than previously imagined. For others, it could pose a deep challenge to anthropocentric doctrines that place humanity at the center of a created order. If we are not the only children of the cosmos, what becomes of our specialness? This wouldn't necessarily diminish our significance, but it would certainly contextualize it, placing us within a broader, more magnificent tapestry of existence. The search for meaning would expand from a terrestrial pursuit to a galactic one, inviting a new era of spiritual and philosophical exploration as we grapple with our place in a potentially populated universe. Scientifically, the impact would be nothing short of revolutionary. A second genesis on Mars would provide the first tangible data point in the field of comparative biology. For the first time, we would have another example of life to study, to compare against the blueprint of every living thing on Earth. We could analyze its biochemistry. Does it use the same DNA and RNA we do? Does it rely on the same 20 amino acids, or has it found a completely different path, an alternative solution to the problem of existence? If Martian life shares our fundamental biochemistry, it could suggest that life's building blocks are readily scattered throughout the cosmos by comets and meteorites, or that the path from chemistry to biology is narrow and predictable. If, however, it represents a completely independent genesis, a separate tree of life with a different molecular foundation, the implications are even more breathtaking. It would suggest that the universe is not just teeming with life, but teeming with different kinds of life, that the transition from non-living to living matter is not a difficult barrier but a common occurrence wherever conditions are right. This single data point would transform biology from a science that studies one example of life into a universal science, allowing us to begin to understand the laws of biology in the same way we understand the laws of physics and chemistry. The discovery would instantly elevate the search for extraterrestrial intelligence from a speculative endeavor to an urgent, paramount human priority. If simple life exists next door, then complex, multicellular life must be possible elsewhere. And if complex life is possible, then intelligent, technological civilizations might not be the stuff of science fiction, but a statistical probability across the billions of habitable worlds we now know fill our galaxy. Funding and public support for missions to the icy moons of Jupiter and Saturn, worlds like Europa and Enceladus with their subsurface oceans, would surge, as they would instantly become the most promising places to look for a second, independent example of life. The ambitious plans to build ever larger space telescopes capable of analyzing the atmospheres of exoplanets for biosignatures would be fast-tracked, driven by the newfound certainty that we are not looking for a needle in a haystack but for a field of haystacks. The mantra would shift from "Are we alone?" to "Where is everyone else?" Ultimately, finding life on Mars would be a profound act of cosmic connection. It would tell us that we are not alone in our loneliness, that the silent void between stars is not so silent after all. It would be a humbling reminder that our planet is not a sealed terrarium, but part of an interconnected, living system that may span the entire solar system and beyond. This knowledge could unify humanity in a way few things ever have, presenting us with a shared, monumental challenge and a common identity, not as citizens of nations, but as citizens of a living planet, newly aware of our neighbors in the cosmic dark. It would be the beginning of a new chapter, not just for science, but for our species, a chapter where we finally step out of our cradle and into a universe that is waiting, full of life and ready to be known. This profound mystery on our neighboring world forces us to lift our gaze from the rust-colored soil of Mars and confront one of the most haunting questions in all of science. If the universe is so vast and so old, teeming with billions of potentially habitable planets, then where is everybody? This is the core of the Fermi paradox, the puzzling contradiction between the high probability of extraterrestrial civilizations and the complete lack of any evidence for them. For decades, the search for answers to this paradox has focused on the stars, on listening for radio signals from distant suns. But the Martian methane mystery offers a radical new perspective, suggesting that the great filter, the hypothetical barrier that prevents life from progressing to intelligence and interstellar travel, might not lie in the distant cosmos but right here in our own backyard. The discovery of even simple microbial life on Mars would have a seismic impact on the equation at the heart of the paradox. It would powerfully suggest that the first step in the chain, the genesis of life from non-living chemistry, is not a miraculous one-in-a-billion event, but a relatively common and predictable process. If life could start independently on two different planets orbiting the same star, then the galaxy must be absolutely saturated with it. This realization makes the silence from the stars even more profound and more disturbing. It would shift the weight of the paradox, implying that the great obstacle isn't the beginning of life, but what comes after. The universe might be full of microbes, but utterly devoid of mathematicians. This is where the nature of the Martian life, if it exists, becomes critically important. Imagine two different scenarios. In the first, we discover that Martian microbes share our same fundamental biochemistry. They use DNA, RNA, and the same set of amino acids. This would be astonishing, but it would suggest that the path from chemistry to biology is narrow and constrained. There might be only one way to build a living cell. If this single blueprint is so powerful that it arises on multiple worlds, then the fact that it only seems to have produced a technological civilization once, here on Earth, becomes even more worrisome. It hints that the leap to complexity, to multicellular organisms, to animals, to intelligence, might be the true and incredibly difficult filter. Now consider the second, even more mind-bending scenario. We find that Martian life is truly alien. It uses a different genetic molecule, a different solvent instead of water, or a completely novel metabolic process. A second, independent genesis would tell us that the emergence of life is not just common, but almost inevitable wherever conditions are vaguely right. The cosmic abundance of biology would be all but confirmed. Yet, if after 4 billion years, this separate tree of life on the planet next door remained stuck at the microbial stage, never evolving beyond simple cells, it would paint a profoundly lonely picture for our own future. It would suggest that while the universe may be a verdant garden of simple life, the evolutionary path to creatures who can look up and wonder at the stars is a treacherous one, littered with dead ends. We wouldn't be missing signals from other civilizations because they're hiding. We might be missing them because they simply never evolved in the first place. The silence of the cosmos would then be the silence of a universe filled with plankton, but no whales. To truly envision what Martian life could be, we need to look no further than some of the most extreme and ancient environments right here on Earth. The prime candidates are not bacteria, but a remarkable group of microorganisms known as methanogens. These are not your typical germs. They belong to an entirely separate domain of life called archaea, representing one of the most primordial branches on the tree of life. Their name gives away their secret talent. They are methane makers. Methanogens are anaerobic, meaning they not only survive without oxygen, they are actually poisoned by it. They flourish in places that would be instantly lethal to almost any other creature, and in doing so, they provide us with a powerful, living model for the kind of biology that could potentially exist on Mars today. Think about the places these extraordinary organisms call home. They are the unseen inhabitants of a hidden world, thriving in the oxygen-deprived mud at the bottom of swamps and wetlands, which is where the marsh gas we sometimes see bubbling up actually comes from. They live in the stomachs of cows and other ruminants, where they play a crucial role in digestion, albeit with the side effect of producing significant amounts of methane. But the most compelling analogues for Mars are found even deeper. Vast colonies of methanogens exist in the deep biosphere, living kilometers below the Earth's surface within porous rocks, where they utilize the tiny pockets of water and chemical energy trapped there. They thrive in the scalding, mineral-rich waters around hydrothermal vents at the bottom of the ocean, and they persist within the permanently frozen soil of the Arctic permafrost. These are not easy places to live. They are margins of existence, and methanogens have mastered them for billions of years. Their metabolism is a thing of beautiful, primal simplicity. They are chemosynthetic, meaning they don't need sunlight for energy. Instead, they feed on a very basic diet of inorganic chemicals that are common throughout the solar system. Some consume simple gases like hydrogen and carbon dioxide, which are plentiful in the Martian atmosphere and soil, and they combine them to produce methane and water as waste products. Others can break down acetate or formate. This is a form of respiration, but it's entirely chemical. They are essentially eating rocks and breathing out a gas, a process that provides them with just enough energy to maintain their simple, ancient way of life. This makes them the perfect candidates for a Martian ecosystem, a world with no oxygen, no sunlight reaching the subsurface, but likely plenty of hydrogen and carbon dioxide produced by geological processes. What makes methanogens such a compelling model is their incredible durability. They are extremophiles in the truest sense, capable of withstanding conditions that we now know exist on Mars. They can survive immense pressure deep underground. Some species are highly resistant to radiation, a critical advantage on a planet with no protective magnetic field. They can endure extreme desiccation, essentially shutting down their metabolism and entering a state of suspended animation for potentially millennia if their water source disappears, only to reanimate when conditions become favorable again. This resilience suggests that if life ever did get a foothold on a warmer, wetter Mars billions of years ago, organisms like methanogens wouldn't have just gone extinct when the planet froze over. They would have done what they have always done on Earth. They would have followed the water and the energy down, retreating into the deep, protected subsurface, where they could continue their slow, steady existence in isolated pockets of briny water, their metabolic pulse reduced to a near standstill but never quite stopping. This analogy transforms the methane mystery from an abstract chemical puzzle into a tangible biological scenario. When we see those sudden, seasonal plumes detected by curiosity, we can now picture a potential cause. A community of Martian methanogens eking out an existence in a dark aquifer deep below Gale crater could be responding to the faint warmth of the Martian summer. That slight increase in temperature might be enough to slightly increase their metabolic rate or to shift the pressure in their underground world, opening a new fissure and allowing a built-up pocket of their metabolic waste, methane gas, to vent suddenly to the surface. The pattern we observe mirrors the biological rhythms we see in Earth's wetlands. It provides a plausible, elegant mechanism for the transient, seasonal behavior that has been so difficult to explain with geology alone. These tiny, ancient Earthlings give us a blueprint, a way to imagine the unthinkable, that the red planet is not a static tomb but a world with a hidden, breathing heart. Of course, the vast majority of scientific discussion rightly focuses on the natural explanations we've explored, but the very nature of a profound mystery invites us to occasionally stretch our imaginations to their absolute limits, to play with the most speculative and remote possibilities. After all, some of the greatest discoveries in history have come from asking questions that initially seemed absurd. So, while we must remain firmly grounded in evidence and the scientific method, let's take a brief, imaginative detour and ask, what if the methane isn't biological or geological in any conventional sense? What if it's something else entirely? First, we could consider the idea of an unknown, exotic chemistry. We base our understanding of how methane is formed on the conditions and elements common on Earth. But Mars is a different world with a different history. Is it conceivable that there are abiotic chemical pathways, perhaps involving unique mineral catalysts or energy sources we haven't yet discovered, that could produce methane in these sudden, sporadic bursts? Perhaps a reaction that only occurs under the specific pressure and temperature conditions found in the deep Martian subsurface, triggered by subtle seismic shifts or the infiltration of supercooled brines in a way that mimics a seasonal pattern. It would be an extraordinary geological process, one that defies our current models, but the universe has a way of being more inventive than we are. Then there's the most speculative yet irresistibly fascinating idea of all, the concept of a technosignature. A biosignature is evidence of life, but a technosignature would be evidence of technology. Now, let's be perfectly clear. No credible scientist is seriously proposing that little green Martians are running a fossil fuel industry. The idea is not about literal aliens, but about challenging our definitions and expanding the boundaries of what we consider possible. Could the methane be an unintended byproduct, a form of industrial waste from a completely non-biological, autonomous process? Imagine a scenario purely as a thought experiment where an ancient, long-dormant technology, perhaps a mining operation or a power source left behind by a visiting civilization eons ago, still operates on some intermittent, malfunctioning cycle, venting this gas as a sign of its decaying function. It sounds like the plot of a science fiction novel, and it almost certainly is, but on a philosophical level, it forces us to confront our assumptions. We are so focused on finding life that we might not think to look for its artifacts, especially if those artifacts don't resemble anything we would build. This line of thinking, while fanciful, serves a vital purpose in the scientific process. It is the ultimate exercise in keeping an open mind. By entertaining even the most outlandish possibilities, we ensure that we don't become so locked into a single paradigm that we miss a truly revolutionary explanation staring us in the face. It reminds us that our knowledge of the universe is still in its infancy, and that the most astonishing truths may be ones we haven't even begun to imagine. The methane on Mars is a real, measurable phenomenon, and the most likely answers lie in the realms of geology and biology. But for a moment, allowing our minds to wander through the farthest reaches of possibility underscores the sheer wonder of this mystery. It's a testament to the fact that we are investigating a new world, and new worlds have a way of delivering surprises that humble our expectations and expand our understanding of what can be. This unfolding detective story on another world does something remarkable. It reaches beyond the laboratories and academic journals to capture the imagination of people everywhere. There's a tangible thrill in checking the news, wondering if today will be the day a rover or an orbiter sends back the data point that changes everything. This isn't a mystery locked away in a textbook. It's a live investigation happening in real time on a planet we can see with our own eyes on a clear night. That accessibility transforms everyone from passive observers into active participants in the greatest hunt of all time, fostering a deep, personal connection to science that few other subjects can achieve. It makes planetary exploration feel less like a distant government program and more like a shared human adventure, a collective holding of breath as we wait for the next clue. This public engagement is a powerful engine for inspiring the next generation of scientists, engineers, and dreamers. A child who follows the journey of the Curiosity rover, who sees the breathtaking images from Jezero crater, or who gets chills hearing about a mysterious methane spike isn't just learning a fact, they are being invited into a story. That story shows them that science isn't a static collection of answers, but a dynamic, thrilling process of asking questions. It demonstrates that the universe is still full of wonders to be uncovered, and that they themselves could be the ones to eventually solve this very mystery. This is how lifelong passions are ignited. The quest for life on Mars isn't just about finding microbes, it's about planting the seeds for future discovery, showing young minds that the most exciting careers are built on curiosity, perseverance, and the courage to explore the unknown. Furthermore, this mystery brilliantly demystifies the scientific process itself. The debate between the biological and geological origins of the methane isn't presented as a conflict or a sign of failure, but as a transparent, collaborative, and rigorous search for the truth. The public gets a front-row seat to see how science actually works, how new data can overturn old theories, how instruments must be validated, and how the entire global community of researchers argues, corroborates, and slowly builds a consensus. This openness makes science more relatable and human. It shows that even the brightest minds don't have all the answers, that they too experience the frustration of contradictory data and the exhilaration of a new lead. This transparency builds trust and showcases the integrity of a process dedicated not to being right, but to getting it right, no matter how long it takes. Ultimately, the Mars methane mystery serves as a powerful reminder of our shared place in the cosmos. It's a question that transcends national borders, political divisions, and cultural differences, uniting humanity in a common, profound wonder. Whether you're a student in Jakarta, a farmer in Brazil, or a software developer in California, the question of whether we are alone is a universal one. This shared investment in a peaceful, collaborative quest for knowledge highlights the very best of what our species can achieve when we work together toward a goal grander than ourselves. The red planet becomes a focal point for global cooperation, a symbol not of conquest but of collective curiosity, proving that the most compelling frontiers are those we choose to explore together. So where does this leave us after years of discovery and debate? We stand before a cosmic riddle, holding a collection of clues that point in two utterly fascinating, yet completely different directions. On one hand, we have the undeniable ground truth evidence from curiosity, mysterious bursts of methane that behave in a hauntingly familiar biological way, appearing suddenly, following a seasonal rhythm, and vanishing with a speed that suggests an active modern process. It's a pattern that on Earth would have us instantly pointing to living microbes, breathing in the hidden dark beneath our feet. The possibility that we are witnessing the faint, gaseous breath of a subterranean Martian biosphere is so profound it feels almost like a revelation waiting to happen. Yet, the universe is a master chemist, and Mars is a world that constantly reminds us not to jump to conclusions. The competing geological theories are equally compelling. The elegant, abiotic dance of serpentinization, where water and rock combine to create methane deep underground, presents a perfectly viable, lifeless explanation. The destructive power of ultraviolet radiation breaking down ancient organics on the surface, or the sudden rupture of billion-year-old frozen clathrate deposits, could just as easily account for the sporadic plumes. The stark null result from the ExoMars Trace gas orbiter adds a crucial layer of complexity, telling us that whatever is happening is local, transient, and being scrubbed from the atmosphere by processes we are still working to understand. This isn't a case of one side having all the evidence. It's a rigorous, healthy scientific debate where both possibilities remain firmly on the table, each supported by strong yet incomplete data. This is what makes the Martian methane mystery one of the most thrilling ongoing stories in all of modern science. It is a true detective novel unfolding in real time on another world. There is no boredom here, no settled answer, only the electric anticipation of the next date, a download, the next paper, the next mission that might finally tip the scales. It embodies the very best of exploration, the courage to ask a profound question and the humility to accept that the universe will reveal its secrets on its own timeline, not ours. The most exciting part is that this story is far from over. In many ways, it's just beginning. The Perseverance rover is right now collecting samples that could contain the fossilized evidence of ancient life, providing context for what might be happening today. The ambitious Mars sample return campaign aims to bring those rocks home within the next decade, where our most powerful labs can interrogate them for definitive proof. And every day, orbiters continue to circle and rovers continue to rove, gathering more pieces of this incredible puzzle. this is your invitation to stay engaged. The search for life isn't a remote activity for a few scientists in lab coats. It's a human journey, and you have a front row seat. Follow these missions as they unfold. Let yourself get excited by a new headline or a raw image beamed back from Jezero crater. Talk about it with your friends and family. Debate whether you think it's microbes or geology. Because that conversation, that shared sense of wonder and curiosity, is just as important as any scientific instrument. It's what drives us forward as a species, to keep looking up, to keep asking questions, and to never stop marveling at the mysteries waiting next door.